Taking flight: a history of naval aviation launch systems. From the earliest days of naval aviation, getting aircraft airborne from the cramped decks of ships posed a significant challenge. Early methods were rudimentary. Pilots relied on sheer daring and unreliable catapults, powered by compressed air or weights and pulleys. These systems severely limited the size and weight of aircraft. This in turn limited their operational range and capabilities. The Second World War marked a turning point with the introduction of hydraulic catapults. These systems offered more power. They could launch heavier aircraft with larger payloads. However, the true revolution came with the advent of steam catapults in the 1950s. These catapults used high-pressure steam from a ship's boilers to propel a piston attached to the aircraft. This innovation became the standard for decades. Steam catapults allowed navies to field faster and more powerful jets. They expanded the role of aircraft carriers in naval warfare. However, even as steam catapults became increasingly sophisticated, their inherent limitations became apparent. They were bulky, maintenance-intensive, and prone to corrosion. Their reliance on a ship's steam system also introduced an element of vulnerability. In the event of a boiler room casualty, the ability to launch aircraft could be compromised. By the turn of the 21st century, it was clear that a new, more efficient and versatile launch system was needed to meet the demands of modern naval aviation. The limitations of steam call for innovation. Steam catapults, while revolutionary for their time, presented a unique set of challenges. Their operation was inherently violent. Aircraft were subjected to immense stress as they were hurled along the deck. This stress reduced the lifespan of aircraft. It also led to increased maintenance requirements. The immense power required to generate the steam also placed a considerable strain on the ship's power plant. This limited the amount of energy available for other ship systems. Furthermore, steam catapults were inherently inefficient. A significant amount of energy was lost as heat. This made them less than ideal in an era of increasing emphasis on energy conservation. The size and weight of steam catapults also posed logistical challenges. They required a large amount of space below deck. This limited the space available for other critical systems such as ammunition storage and living quarters. Their maintenance required specialized skills and equipment. This added to the logistical burden of operating an aircraft carrier. As the demands on naval aviation grew, the limitations of steam catapults became increasingly apparent. The need for a more efficient, reliable, and versatile system was clear. This need drove the development of a new generation of launch technology, the Electromagnetic Aircraft Launch System, or EMALS. EMALS, a new era of electromagnetic launch. The Electromagnetic Aircraft Launch System, or EMALS, represents a paradigm shift in naval aviation. Unlike its steam-powered predecessor, EMALS uses electromagnetism to launch aircraft. It utilizes a linear induction motor, a series of electromagnets along a track. The system includes energy storage, power conversion, and system control. The motor's moving magnetic field propels a carriage attached to the aircraft. Energy storage accumulates and releases power for the motor. Power conversion transforms the ship's power for the motor. System control manages the entire launch process, ensuring precision and safety. Section 4. EMALS advantages: efficiency, flexibility, and force. EMALS offers a compelling array of advantages over traditional steam catapults. These advantages are transforming the landscape of naval aviation. One of the most significant is its increased efficiency. EMALS converts over 80% of the energy it draws into kinetic energy. This is a stark contrast to steam catapults, which lose a significant portion of their energy as heat. This efficiency translates into a reduced burden on the ship's power plant. This frees up valuable megawatts that can be directed to other ship systems. This is particularly crucial as modern warships increasingly rely on sophisticated electronic systems that demand vast amounts of power. Beyond its efficiency, EMALS offers unparalleled flexibility. The system can be fine-tuned to launch a wide range of aircraft. This includes everything from lightweight drones to heavy fighter jets. This is in stark contrast to steam catapults, which require manual adjustments to launch different aircraft types. EMALS' ability to precisely control the launch force also reduces stress on the aircraft. This translates into a longer lifespan for carrier-based aircraft and reduced maintenance requirements. This is a significant advantage as maintaining aircraft is a costly and time-consuming endeavor. Furthermore, EMALS is much quieter than its steam-powered predecessor. This reduced noise signature is advantageous from a tactical perspective. It makes it more difficult for adversaries to detect carrier operations. This is crucial in an era of increasingly sophisticated anti-ship missiles. Section 5. Challenges on the flight deck. EMALS implementation and criticism. The development and implementation of EMALS has not been without its challenges. As with any new technology, there have been hurdles to overcome. The system's complexity and sophistication have led to delays and cost overruns. This has drawn criticism from some quarters. One of the primary criticisms leveled at EMALS is its cost. The system is significantly more expensive to install than traditional steam catapults. This has led some to question whether the benefits of EMALS outweigh its high price tag. However, proponents argue that the long-term benefits, such as reduced operating costs and increased efficiency, will ultimately offset the initial investment. Another challenge has been the need to integrate EMALS into existing carrier designs. Retrofitting older carriers with EMALS is a complex and costly undertaking. This has led some navies to opt for new carrier designs that incorporate EMALS from the outset. Despite these challenges, EMALS has demonstrated its potential. As the technology matures and becomes more widely adopted, it is likely that many of these initial challenges will be overcome. The long-term benefits of EMALS in terms of efficiency, flexibility, and capability are undeniable.